All right, so we'll continue with the next lecture on robust auction design. So just to remind you, in the first lecture, we reviewed some basic and fundamental results in classical mechanism design. And then in lecture 2, we introduced the Wilson critique of mechanism design, where we assume a lot of things to be common knowledge that perhaps should not be assumed to be common knowledge. And that motivated ex post implementation as an implementation concept. And we motivated that both from an implementation theoretic perspective and also from a max-min perspective. And we solved for the optimal ex post revenue maximizing ex post auction, revenue maximizing ex post implementable auction. So there were two crucial assumptions that were used heavily in the previous lecture. One is that the allowed beliefs of the agents didn't have to satisfy the common prior assumption. And another is that the bidders have private values. So each bidder knows exactly what their own value is for being allocated the good. So each of these assumptions is controversial. If you had arbitrary departures from a common prior, then agents would have an incentive to make bets with each other about probabilistic outcomes that they fundamentally disagree with one another on. And, of course, the extent of those bets that people would be willing to make depends both on the departure from the common prior and also their degree of risk aversion. But nonetheless, extreme departures from the common prior seem like they might not occur in practice. With regard to private values, there are a lot of settings where it seems unreasonable to think that the bidders know exactly what the good is going to be worth, and that other bidders might not have some information that's payoff relevant to them. So for the next two lectures, we're going to reverse course on both of those assumptions, impose the common prior assumption, but allow for interdependence in values. And actually, for a fair amount of the analysis, we're going to go to an opposite extreme of private values and assume that the bidders have pure common values. So all of the bidders have exactly the same true value for the good, but they have differential and private information about what that common value is. Some of the results generalize beyond the case of common values, but this is an important benchmark for us. Okay. An additional difference is that while previously we had been assuming that the seller gets to pick the equilibrium, as demonstrated by our repeated use of the revelation principle, or as reflected in our repeated use of the revelation principle, now we're actually going to look for robustness with respect to equilibrium selection as well. What if an unfavorable equilibrium of the mechanism gets played? I want to flag that, all of these differences and assumptions that we're making starting in this lecture, there's no a priori reason why all these assumptions have to go together. You could say, look at interdependent values, but also allow for non-common prior beliefs, or you could impose the common prior assumption, but maintain the hypothesis of private values. So the reason for moving in this direction together is simply because when you move all of these pieces simultaneously, it leads to a very tractable and powerful theory. All right, so the new high-level goal is going to be, and I should say that we're going to pursue the max-min perspective going forwards, rather than ex post implementation. So we're not going to insist on the mechanism being ex post implementable. We're just going to look for mechanisms that provide favorable revenue guarantees across lots of informational environments. Okay, so that's the new high-level goal. Characterize auctions that are going to perform well regardless of the bidder's common prior beliefs, and also regardless of which equilibrium is played. So a preliminary step in that agenda is to develop a tool for characterizing, for a fixed mechanism, what are the outcomes that could arise for some common prior information structure in some Bayes-Nash equilibrium. Once you have this tool, then you can think about, well, which mechanism would we want to use in order to achieve favorable outcomes across all of these outcomes, favorable revenue across all of these outcomes. So this tool that we're going to use is called Bayes correlated equilibrium, due to Bergman and Morris 2013 and 2016. Okay, so here's the basic environment. And again, I'm going to introduce the solution concept in a fairly abstract setting, and then later we'll specialize it to the auction design context. So there's a payoff relevant state, theta, as before. n players. A game form consists of actions for each of the players and a utility function that maps actions and action profiles and payoff relevant states into real numbers. We're going to denote this by G when we're treating it as an abstract fixed game. Later, I'll probably call this a mechanism and denote it by M, but mechanisms and game forms are going to be used interchangeably throughout this lecture. A common prior information structure, as we said at the beginning of the last lecture, can be described as sets of signals for each of the players and a joint distribution over signals and states. And then the interim beliefs of the players conditional on their signal are derived by Bayesian updating from this prior. So together, a game form and an information structure constitute a Bayesian game, and player I's strategy in that game is just a mapping that takes their signals into a distribution of their actions. So if we fix a tuple of strategies for the bidders, then we can compute an expected payoff for player I, which is just the expectation of their utility, where that expectation is taken over states and signals, and then the conditional distribution of the actions given the states implied by the strategies, where this is interpreted as the product distribution like that. So Bayes-Nash equilibrium is simply a profile of strategies such that for each player and for each alternative strategy, their payoff, if they follow the proposed strategy, is greater than what they could get if they deviate and others follow their proposed strategies. So the high-level question that we're going to ask next is, what are the outcomes of this game form that are consistent with Bayes-Nash equilibrium being played for some common prior information structure? So to answer that question, of course, I have to be a little bit more specific about what an outcome means. So an outcome in this context is going to be a joint distribution over payoff relevant states and actions. So we're integrating out the purely informational aspect of the interaction, which is the signal. So if you have an information structure, common prior information structure, and a Bayes-Nash equilibrium, in fact, any strategy profile, then those together would induce a particular outcome, which is obtained just by integrating out the signals. Okay, and a Bayes correlated equilibrium, an outcome is a Bayes correlated equilibrium if it satisfies these linear inequalities here that are called obedience constraints. So effectively, what these constraints say is that you can interpret a Bayes correlated equilibrium as an information structure where the signal is actually an action. And these obedience constraints are saying that in that information structure, it is a Bayes-Nash equilibrium for the players to take an action that's equal to their signal. So obedient play is a Bayes-Nash equilibrium of this revelation information structure. This is kind of a revelation principle for, well, let me come back to that in a second. Okay, so here is the main theorem regarding Bayes correlated equilibria. An outcome, sigma, is a Bayes correlated equilibrium of this game form if and only if it is induced by some common prior information structure and a Bayes-Nash equilibrium of the resulting Bayesian game. Okay, so this is a kind of revelation principle for information. It says that if you're interested in what are the outcomes that could occur across all common prior information structures in Bayes-Nash equilibria, it is without loss of generality to restrict attention to these direct information structures where a signal is simply an action, a suggestion of an action to play in the game form, and playing the action that is recommended is a Bayes-Nash equilibrium. Okay. And of course, why is the revelation principle hold here? It's similar to why it held in the mechanism design context considered previously. When we're constructing an outcome, we can pick the information structure to be what we want, whatever we want. So we have a rich set of information structures that are available. And also, if we want to construct a particular outcome, we can pick any equilibrium that we want. So if you have rich set of information structures that are available and you can pick the equilibrium, then a revelation principle for information will hold. Okay, so this proof is not very difficult. It's very similar, actually, to the classic proof that correlated equilibrium captures Nash equilibrium for all correlation devices. So in one direction, the if direction, we want to show that if you have an outcome that is induced by an information structure in a Bayes-Nash equilibrium, that implies that the induced outcome is a Bayes correlated equilibrium. Well, what you have to do is show that that outcome satisfies those obedience constraints. But if not, if one of those obedience constraints was violated, then that is equivalent to saying that there is a profitable deviation for the player for whom the obedience constraint is violated, where whenever they would have played some action AI, just switch to an AI prime instead, where that AI and AI prime correspond to the violated obedience constraint. In the other direction, you start with a Bayes correlated equilibrium, and you want to show that it is induced by some common prior information structure in a Bayes-Nash equilibrium. Well, I've kind of already told you what the construction is that achieves that. Pick the information structure so that signals are actions, and the joint distribution over states and signals is just given by sigma, the outcome itself. Then the strategies are this identity mapping, where when your signal is AI, you put probability 1 on playing AI. And then in the equilibrium conditions, verifying that these strategies are a Bayes-Nash equilibrium, follow immediately from the obedience constraint. When your signal is AI, there can't be an action that yields a higher expected payoff than AI. Okay, so the key difference, again, relative to lecture 2, is that when we use Bayes correlated equilibria as our solution concept for a game form or a mechanism, we're now imposing the common prior, because there is a big joint distribution that all players are commonly using to compute their payoffs. But I should emphasize that this is still much more general than lecture 1, than the information structures that were considered in lecture 1, where we were fixing a particular information structure, which in all instances considered there satisfied the common prior assumption. But now we're allowing for much richer signals, in addition to arbitrary information about a payoff relevant state. There's no restriction like in Bergman and Morris, for example, that the players know a payoff type, and that those payoff types are the payoff relevant state. Okay. In addition, a key difference relative to both lecture 2 and lecture 1 is that Bayes correlated equilibrium allows for an arbitrary equilibrium to be played rather than, say, the designer preferred equilibrium. From a more pragmatic perspective, Bayes correlated equilibria are analytically quite tractable. They're probability distributions, so elements of a linear space, and they're contained in the intersection of this finite collection of linear obedience constraints. So that's in everything that we have to tell you subsequently about the application of Bayes correlated equilibrium in robust auction design. Of course, that analytical tractability is at work under the hood. So it's and one final comment. So in this theorem that I just presented, there were no restrictions on the distribution of theta. It was allowed, so you could have the fundamental vary across Bayes correlated equilibria. In applications, it's often useful to further discipline the set of Bayes correlated equilibria by imposing some marginal restrictions on the distribution of theta, the payoff relevant state. And that way, when you're comparing outcomes across Bayes correlated equilibria, you're basically seeing the effect of information and strategic considerations, not differences due to different fundamentals. So for example, if revenue is varying, revenue will not be varying because the values are being changed from an ex-ante perspective, but just because the player's information about those values or the way they behave on that, act on that information is changing. Okay, so we're going to apply.
I have a question about this. So, there are these computational results about correlated versus Nash equilibria, right? Suggesting that computing Nash equilibria can be hard, and computing correlated equilibria, you do that with a linear program. Is there some sense in which this project that you're doing, that you're expositing here, would be less tractable if instead of optimizing over Bayes correlated equilibria, you were using some more constrained construction?
Probably. I mean, so if you can optimize over information as well, then there's no difference, obviously, because optimizing over Bayes correlated equilibria is the same as optimizing over information structures and Nash equilibria. So if you jointly imposed some restriction, if you added restrictions on information as well as went with a more restrictive solution concept like Nash equilibrium, then I think a lot of the linear structure of the problem would break down.
So almost here, it's the agnosticism about information that is buying you tractability.
Absolutely. And I think that's a general principle throughout robust auction design and probably elsewhere in the world as well, that the larger is the space of things that you're optimizing over, then you have freedom to find simple solutions to complex problems. So whereas analyzing a particular mechanism like the first price auction can be incredibly complicated if you fix just an arbitrary information structure, if instead you solve for, say, Bayes correlated equilibria that minimize expected revenue, that will end up having a lot of structure. So having a large space of things that we're optimizing over works in our favor in that sense. Okay, so we're going to apply this Bayes correlated equilibrium methodology to first price auctions. This is kind of a warm-up exercise, or at least so it seems, because right now we have no reason to think that first price auctions are optimal in any sense, but they are they're a classic mechanism that's considered a good approximation for lots of selling mechanisms that are used in practice, and it's probably the most well-studied Bayesian game in all of game theory and mechanism design. Okay, so this is following the analysis of Bergman, Brooks, and Morris 2017. So we're going to assume that the bidders have a pure common value for the good being sold, which is distributed according to this known F. And this is going to be fixed throughout our analysis, as I was saying, in terms of applying Bayes correlated equilibria with restrictions on the distribution of the payoff relevant state, which here is this common value. So the bidders are going to compete in a first price auction. What does that mean? They submit bids, which are non-negative numbers, and the high bidder is going to win the good and pays what they bid. And ties are broken, say, uniformly. So there's no reserve price or anything in this auction, meaning that the good is always going to be allocated. The bidders all have exactly the same value for the good being sold. So there is no efficiency consideration in who wins the auction, which means that total surplus in any information structure and in any Bayes-Nash equilibrium, total surplus is going to be the same, and it's just the efficient surplus, which is the ex-ante expectation of the value, I'll call V hat. So what does depend on information and equilibrium is how this surplus is split between the seller and the bidders. And at one extreme, it could be that all of the information that the bidders have is public, in the sense that there's a signal that everybody sees, and there's common knowledge of that signal realization. So in that case, the bidders have no private information. They are effectively playing a complete information Bertrand game, and they'll just bid the price up to the interim expectation of the value. Bidders compete away all their rents, and expected revenue is V hat. Okay, so when we're interested in understanding the range of revenue outcomes across all information and Bayes-Nash equilibria, one extreme we've pinned down, it could be that revenue could be at most V hat, and it's possible for it to be V hat in the case of public information. So the next question is, well, what about minimum revenue? What could that be? Now, bids have to be non-negative, so revenue also has to be non-negative. One thing you might conjecture is, well, maybe it could be zero. Maybe there's information in an equilibrium in which the bidders just compete the price or don't compete at all. But that can't happen, basically, because if you were in a Bayes-Nash equilibrium where everybody was bidding zero, then any one of the bidders could deviate to bidding some epsilon and go from winning part of the time when they win a tie break to winning all the time. And of course, on average, the value is V hat. And so there would be an enormous gain from that small increase in your bid. Okay, so this kind of heuristic argument says that, well, minimum revenue across all Bayes correlated equilibria can't be zero, and kind of the relevant equilibrium constraints that are preventing revenue from falling too low would be the incentive for bidders to deviate up if the distribution of winning bids was too low. Okay, so we're going to use BCE methodology to characterize exactly what is minimum revenue in first price auction, in this common value first price auction across all information structures and equilibria. Okay, so it turns out that, of course, if we were using base correlated equilibria, then as I introduced it previously, we should be looking at the joint distribution over all of the bids and the common value. But it turns out that to answer this question, we can, without loss, look at certain marginals and conditional distributions of the base correlated equilibria. So that's what I'm going, but the underlying methodology is the same in that we're going to be using certain obedience constraints in order to characterize minimum revenue. Okay, so what are the particular objects that we need? First one I'll call H of A given V. So this is the probability that the highest bid is less than A, conditional on the value being V, the common value being V. H of A is the ex ante distribution of the highest bid. And then HI of A given V is the probability that bidder I wins and the winning bid is less than A. So this last one is not a cumulative probability distribution because we're multiplying by the probability that bidder I wins. But nonetheless, it's a useful object for our characterization. Okay. So these objects are rich enough to compute bidder's surplus in equilibrium. If you had an equilibrium and these were the induced conditional distributions of winning bids and who wins, then bidder I's surplus is simply going to be the expectation across all common values of the winning bid, of the value minus the winning bid on the event that bidder wins the auction. And the likelihood of X being the winning bid when the value is V and bidder I winning is exactly this expression here. Okay. So, of course, not any winning bid distribution could arise in an equilibrium under a common prior information structure. So we're going to have to bring equilibrium conditions in, and we're going to do it by looking at this particular family of incentive compatibility conditions that correspond to what I'll call uniform upward deviations. So this is a particular kind of deviation in the strategic normal form of the first price auction, where you switch from whatever B strategy that you're using to a particular B prime. And how it works is if a bidder uniformly deviates up to some A, then they bid A whenever they would have bid a number less than A in equilibrium. But if they were going to bid more than A in equilibrium, they just keep bidding A. Okay, that's the nature of a uniform upward deviation to A. Okay, so as long as the ex ante distribution of the winning bid, H, doesn't have an atom at A, then we can easily compute what the surplus is from such a deviation. And it's given by this expression here. So why is that? Well, this is the event that before this deviation, the winning bid would have been a number less than A. Okay. Now, the bidder who's deviated is bidding at least A. So they're definitely going to win in that circumstance. And, they're going to win with a bid of A, because the winning bid could have been less than A only if this bidder themselves, the deviator, were bidding less than A in equilibrium. And in that situation, this bidder has deviated up to A, and so now they're going to win. Okay. On the other hand, it could have been that in equilibrium, the winning bid would have been greater than A. And then there are two possibilities. Either the deviator was the one who was going to win with the bid greater than A, in which case this is the surplus they're going to get. And then this deviation doesn't affect their behavior, so they would still win with whatever bid they were going to make before. Or it could be that some other bidder was going to win in equilibrium. But in that case, whether or not this deviator, this bidder who's deviating actually changes their bid, they're still going to lose the auction, because at best they've deviated up to A, which is still not a large enough bid to change the outcome of the auction. Okay, so this is the correct expression for the surplus of a bidder who's uniformly deviating up to A. And this is everything that I just said. Okay, so of course, if this distribution of the winning bid is induced by some Bayes-Nash equilibrium in some information structure, it must be that no bidder wants to uniformly deviate up to A. And that's exactly captured by this inequality here. So a little rearranging and integration by parts would give us an equivalent formulation of this uniform upward incentive constraint. Okay, so next I want to, what we're going to do basically is characterize lowest winning bid distributions that satisfy these uniform upward incentive constraints. And it's going to turn out that those exactly coincide with minimum revenue in the first price auction. So what do I mean by smallest winning bid distributions that satisfy these constraints? So I mean smallest in the sense of first order stochastic dominance. So if you have two cumulative distribution functions, f and f prime, no relation to the prior over the value, by the way, then f first order stochastically dominates f prime if f of x is less than or equal to f prime of x for every x. So an equivalent characterization is that for any non-decreasing function, the expectation of that function under f is greater than or equal to the expectation of that function under f prime. Intuitively, f has shifted mass to the right relative to f prime. So this is a partial order on probability distributions. Okay, so here is our main theorem on BCE in the first price auction. So there's a particular function. I'm going to define this particular function, B star, which is a function of the common value. And I want you to think of this as a winning bid when the common value is V. Okay, so suppose that when the value is V, the winning bid in the auction is given by B star of V. And then H star of A is the associated cumulative distribution of the winning bid if, in fact, when the value is V, B star of V was the winning bid. Theorem: if H is a winning bid distribution that is induced by some information structure and some Bayes-Nash equilibrium, then H first order stochastically dominates H star. Moreover, there exists an information structure and a Bayes-Nash equilibrium B that induce H star, and the marginal of pi on V is F. So in other words, this H star is the minimum winning bid distribution that could arise in the first price auction when the distribution of the value is given by F. Okay. And immediately that gives us a characterization of minimum revenue in the first price auction across all common prior information structures in Bayes-Nash equilibria, which is just the expectation of B star of V under F. Okay, so the argument is quite involved, and I'm not going to present it in its full glory, but I'm going to give you a brief sketch. So we could lower bound equilibrium H by showing that there is a minimal H that satisfies those uniform upward incentive constraints. And a next step is that those constraints are actually linear in the distributions, and that linearity means that it's without loss to look at symmetric solutions. If you had a collection of HI distributions that satisfy those constraints, and if you average them, then you would also have conditional winning bid distributions that satisfy those constraints. The next step, so you can, without loss, restrict attention to distributions of winning bids in which those uniform upward incentive constraints, in which the winning bid, I should say, is perfectly positively correlated or comonotonic with the value. So why is that? Well, it relates to the particular form of these uniform upward incentive constraints. But essentially, this side of the equation does not depend on the correlation structure between values and winning bids. So the correlation structure only appears here. And it turns out that if you hold fixed the ex ante distribution of the winning bid, this expression is minimized when the value and the winning bid are perfectly comonotonic. Okay, so you can look at comonotonic solutions. And then last step, The last step, of course, once you know that they're comonotonic, it's without loss to parameterize the winning bid distribution as a function that just says for every common value, what will be the winning bid. And and then one can show using a contraction mapping argument that there is a unique smallest winning bid function that satisfies those uniform upward incentive constraints, and it's that B star that I introduced as part of the theorem. Okay, so that shows these steps together show that the H star is a lower bound in the sense of first order stochastic dominance on any equilibrium winning bid distribution. So the last step is just to show that it's a tight lower bound, that it is actually that H star is itself an equilibrium winning bid distribution. And for that, we have to construct the information structure and the equilibrium that induce that H star. So here is the form of the worst case information structure, worst case for the purpose of suppressing revenue, of course. So the signals are just going to be, you could think of them as noisy observations of the value. And these signals are actually independent, and they're drawn from this distribution, f to the 1 over n. Why f to the 1 over n? Well, because if these independent signals are distributed according to f to the 1 over n, then the highest of the signals will be distributed according to this raised to the power n, which is just f. So in other words, with this distribution over the signals, the distribution of the highest signal is equal to the distribution of the value. And in fact, in this information structure, the highest signal is equal to the value. Okay, so equivalently, an equivalent way of describing this information structure is that there's a randomly selected bidder who gets to observe the value, and then all of the other bidders see lower signals, which are distributed according to this truncated distribution independently. Okay, so
Ben, this sounds like it should be connected to the winner's curse somehow, but I can't quite see how.
So good. So it's well known that the adverse inference that can come from winning the auction could depress bids relative to a comparable environment where there is no inference about the value of the good from the fact that you won. So in this information structure, suppose that you had a monotonic pure strategy equilibrium of the first price auction on this information structure. Then there's kind of an extreme adverse inference about the value from learning that you had the high signal. Because before you know whether or not you had the high signal, all you know is that your signal is a lower bound on the value, because the value is the highest of the signals. But then if you learn that you have the highest signal, the conditional support of the value collapses to just your signal. So there is a sense in which this information structure has the most extreme winner's curse effect, just as expressed as depressing revenue. But you could think of why it depresses revenue so much as being linked to that extreme adverse inference about the value. That is related to the next observation. Okay, so we have to say, what is the equilibrium that together with this information structure induces H star? And it turns out to be exactly B star, that winning bid function that we introduced in the theorem. That B star is a symmetric pure strategy equilibrium of the first price auction under this information structure. And in fact, this B star is also the equilibrium of the first price auction in a different independent private value model where bidders interpret their signals as their values. So in other words, in this equilibrium, bidders treat their signals as if they are private values rather than noisy signals about the common value, which again speaks to the adverse inference and the extent of the bid shading. In general, your signal is much less than, or is less than the conditional expectation of the value. It's the lower bound of the support of the value. Okay, so there's something deep there in that connection. Basically, if you think about a bidder who's thinking of deviating to a lower bid, their incentives look exactly the same if their signal is the value or if the signal is just the lower bound on the value, because if you're thinking of deviating to a lower bid, you will only win after that deviation in the event that your signal was the highest, in which case it really is the value. Okay. incentives look different for a bidder who's thinking of deviating to a higher bid, but you can show in that situation that actually bidders are indifferent to all upward deviations, as of course they would have to be in an information structure in a Bayes-Nash equilibrium that makes all of those uniform upward incentive constraints bind as they do at this critical distribution H star. Okay, so I feel like I'm dramatically behind schedule, so I'm going to have to move faster through some of this material. So of course, we were just analyzing the first price auction as, you know, an interesting case study in minimum revenue across Bayes correlated equilibria. But it turns out that the first price auction is actually robustly optimal in the sense of maximizing minimum revenue across all Bayes correlated equilibria if we restrict attention to a certain class of mechanisms. So I'm going to describe that class of mechanisms now. A mechanism, which again is just another name for a game form, is standard if the actions in the mechanism are just real numbers. The bidder who submits the highest bid or action is going to be allocated the good, with ties broken in a way that we don't really care. And the last requirement for being a standard mechanism, if you take that mechanism and you analyze it in a symmetric independent private value model, then that mechanism has a monotonic pure strategy equilibrium, okay, in which the equilibrium bidder surplus is non-negative. So some examples of mechanisms that fall into this category: first price auctions, obviously second price auctions, all pay, English auction, combinations of those, Dutch auctions. So all of those, actually, do I want to say English and Dutch? I don't want to say those, because for those, the strategy space really should properly be considered as richer. But certainly first price, second price, all pay auctions, and combinations of those all work as standard auctions. Okay, so this tool is going to be the glue that allows us to compare revenue in BCE and standard auctions to, or the bridge, I should say, that allows us to compare minimum revenue across all BCE and standard auctions to the first price auction. So suppose that a mechanism is standard and B is a symmetric and monotonic pure strategy equilibrium on the independent private value type space, where again, values are distributed according to F to the 1 over N. Then B is also an equilibrium at I star, which is the revenue minimizing information structure for the first price auction. So why is that? Well, you know, the allocation that is induced by this strategy profile on the independent private value type space is the same as that which is induced by the monotonic pure strategy B star of the first price auction. So the revenue equivalence theorem then tells us that the interim expected transfer of each bidder under the mechanism M is equal to the interim expected transfer in equilibrium under the first price auction up to a constant. Okay, so this T star is the interim expected transfer in the first price auction if you follow these, if everyone follows these equilibrium strategies, and if your signal is SI. Okay. So now let's denote U of SI prime, the payoff in the mechanism M in the IPV type space when the bidder with signal SI bids B of SI prime. Sorry, in the type space, I said type space, but I really meant information structure, I star. Okay, and UFPA is the corresponding object in the first price auction. Well, then we know that up to this constant, actually the utility in the mechanism M and the utility in the first price auction are the same, because you're getting the same allocation if these strategies are followed, and you're also getting the same interim transfer up to a constant. Okay, but because the strategies B star are in equilibrium of the first price auction in this information structure, we know that actually the type SI is getting their highest payoff when they act as SI versus any other SI prime. And that implies that the same is true in the mechanism M on the information structure I star. So this says that in the mechanism M on the information structure I star, there is no way to achieve a higher payoff by mimicking a different signal. Okay, so the last thing that you have to just check is that bidders wouldn't want to deviate to any bids that are not made by some type in equilibrium. And for that, you need to appeal to the definition of standard that the high bidder is going to win the good. So, if there were any bid that's outside of the support of equilibrium bids, there's got to be another bid that is used in equilibrium, results in the same winning probability and a weakly lower transfer, which is, of course, why bidders were not using this out of support bid or not tempted to use that out of support bid in the IPV environment. Okay, and using that, you can conclude that actually all deviations are unattractive from the strategy B in the Bayesian game MI star. Okay, so with that strategic equivalence result in hand, that immediately gives us this characterization of max-min revenue in standard mechanisms. So if M is a standard mechanism, then minimum revenue across all BCE in the first price auction, pi FPA, is greater than minimum revenue across all Bayes correlated equilibria of this standard mechanism. So among all standard auctions, the first price auction maximizes minimum revenue across all Bayes correlated equilibria. And why is that true? Well, for any standard mechanism, there's an equilibrium, a monotonic pure strategy of the equilibrium, symmetric monotonic pure strategy equilibrium of that mechanism on the IPV type space. And by the proposition, that's also an equilibrium on I star. Okay. But in each of these games, these strategies are going to induce the same revenue because you're using the same strategies and the game form is the same. So let's call that revenue pi. But pi FPA is the revenue from the equilibrium B star from the first price auction on the independent private value type space. And we know that actually that's maximum revenue among all incentive compatible and individually rational direct mechanisms on that independent private value type space. So it must be that pi is less than or equal to pi FPA. And so now we've exhibited an information structure and an equilibrium in which revenue in this mechanism is lower than that than pi FPA, and a fortiori infimum revenue of the mechanism M across all Bayes correlated equilibrium must be less than pi FPA as well. So this theorem is a kind of robust revenue ranking. It's saying that the first price auction has a greater revenue guarantee across all Bayes correlated equilibria than any other standard auction. For example, the second price auction. Of course, we didn't need this theorem to tell us that minimum revenue in the first price auction is greater than that of the second price auction, because regardless of the information, second price auctions have low revenue equilibria where, say, one of the bidders bids V bar, the highest possible value, and all of the other bidders bid 0. But what is perhaps more surprising is that there's no way of perturbing the second price auction that preserves its standardness, at least, and results in it outperforming the first price auction. So in particular, convex combinations of first and second price auctions all have lower revenue than, in the worst case, than the first price auction. A brief aside. So, a classic result in game theory is that in affiliated values environments, you get the opposite ranking. English and second price auctions generate more revenue than first price auctions. Whereas now, when we're using this robust criterion of looking at the minimum across all Bayes correlated equilibria, we find that first price auctions do better than English and second price auctions. And so why is that? Well, and that's in spite of the fact that actually this worst case information structure is affiliated. So it is covered under Milgram and Weber's revenue ranking. But there's no contradiction there, because in Milgram and Weber, that revenue ranking is strict only when signals are correlated, and signals are independent on this information structure I star. Of course, it also depends on the selection of particular equilibria that are constructed by Milgram and Weber. So if you combine these observations, you could actually get the following result. If you select the Milgram and Weber equilibria of the second price in the English auctions, and if you restrict attention to symmetric affiliated values information structures, then the three mechanisms, second price auction, first price auction, and the English auction, are all revenue guaranteed equivalent, and they all have a common revenue guarantee, which is pi FPA. Okay, another remark. So similar, in the last lecture, we talked about the model of Chung and Ely, where the optimal ex post mechanism and a particular worst case information structure form a saddle point. And there's a similar structure here, where the first price auction together with the information structure I star are a saddle point. You know, the first price auction is guaranteed to produce revenue of at least FPA, pi FPA, in all information structures and equilibria. And on this information structure I star, no standard mechanism can achieve more revenue than pi FPA in Bayes-Nash equilibrium, in any information structure in equilibrium. Okay, so of course, we have this restriction to standard mechanisms. And the last question we're going to ask and answer in this lecture is, well, could this actually be a saddle point for the unrestricted problem? You know, what if you allowed for non-standard mechanisms to be used? Could the first price auction still be optimal in that more general problem? And the answer is no, actually. So let me explain why. So let's just look at a simple numerical example. If the value were uniformly distributed between 0 and 1, then you can calculate what this winning bid function is, and it ends up being linear. Okay, and the highest winning bid ends up being n-1 over 2n-1. So the minimum winning bid is going to be in the distribution H star is a uniform distribution between 0 and n-1 over 2n-1. This converges as n goes to infinity to uniform on 0 1/2. Okay, so the limit revenue and limit bidder surplus are each a quarter. Now, a quarter is less than the total surplus, the expected value of 1/2. So that means that the bidders are still getting rents in the limit, and revenue is bounded away from this upper bound, which is, you know, a little bit surprising because there are classic results on first price auctions with large numbers of bidders in which you get asymptotic full surplus extraction in the limit. But those results depended on the restriction to certain classes of information structures like the mineral rights model. And that's why you can, if you allowed for richer information structures like I star, then the bidder's rents wouldn't go to 0 in that limit. Okay. Du 2018, Songs's paper constructs a sequence of mechanisms such that when you take the limit as the number of bidders goes to infinity, expected revenue converges to V hat, regardless of the exact distribution of the value. Okay, so that means that even with finite n, it has to be that this revenue guarantee of the first price auction is improvable if you use non-standard mechanisms. Because if it weren't, then there would be no way to get close to V hat when n is large. So the last thing I'll do is explain what those mechanisms are and how they work, and then that'll be the last result for this lecture. So consider the following sequence of mechanisms. So in each of these mechanisms, an action is just a number between 0 and 1, and the allocation and the transfer are structured as follows. So for the allocation, let's suppose that we've ordered the actions of the bidders in this way. So you could fix ideas and say that A1 is bigger than A2 is bigger than AN, say like that. Then the allocation of bidder I is equal to this sum. So what does this sum mean? Here's an interpretation. It's as if the good is composed of a continuum of pieces indexed by numbers between 0 and 1. And the action AI means I want to buy the pieces that are indexed by X's less than my action. I want to buy the pieces X less than AI. And each piece is going to be divided equally among the bidders that demand it. So if AN is the lowest, then it means that the X's below AN are demanded by each of the bidders. And so those increments of the good, or those pieces of the good, are going to be divided equally among all N bidders. And then pieces between AN-1 and AN are going to be divided between N-1 bidders, and so on. Okay, so that's how the allocation works. And the transfer satisfies this particular exponential form. Your transfer only depends on your own action, and it's proportional to the exponential. It's affine in the exponential of your action. So I'll explain. It'll be clear in a slide why this functional form for the transfer is interesting, useful. Okay, so here is Songs's theorem. In any Bayes correlated equilibrium of Mn, revenue is equal to V hat plus a term that goes to 0 at a rate of 1 over log n. Okay, so when n is large, expected revenue in all Bayes correlated equilibria has to be close to V hat. So why is that? Well, if we fix a Bayes correlated equilibrium, sigma, then expected revenue in the mechanism is just the sum of these transfers. Okay. Now, crucial fact about that transfer rule is it satisfies this differential equation. So that allows us to relate expected revenue to the expected derivative of the transfer with respect to each bidder's action. So if we just make a substitution into here, we get this equivalent expression for expected revenue. Now, why is that useful? Because this is going to allow us to link expected revenue to local incentives in the auction. And I'll explain how that works. So a step that I'm not going to discuss in detail, you can show that given the particular parameters that we chose for the transfer rule, bidders will not want to bid 1. They'll always be bidding, they'll bid less than 1 with probability 1 in any equilibrium. It's too expensive to bid 1, basically. Moreover, in any Bayes correlated equilibrium, this inequality has to be satisfied. So what this is saying is that on average across the bidders and on average across all actions and values, the gain from an infinitesimal increase in the bid is non-positive. So this is saying that bidders don't want to deviate locally upward on average. And if this constraint were violated, then it would mean that there's some bidder and some positive measure of actions that are taken by that bidder for which they would benefit by increasing their action by a little bit. So if we combine that previous expression for revenue in terms of the derivative, the sensitivity of transfers to actions with this inequality, we get a lower bound on profit in any Bayes correlated equilibrium. That profit has to be greater than or equal to this integral of values times allocation sensitivities, basically. And then the last step is that because of the particular functional form chosen for the allocation, it's possible to lower bound those allocation sensitivities. And in fact, the sum of these allocation sensitivities is at least the log of n plus 1. So if we combine all of these observations, we start with transfers, which are linked to local incentives through the form of the transfer rule, which are then linked to the allocation through local obedience constraints. And then finally, we achieve this lower bound using properties of the allocation rule. And then if we take the limit of this expression as n goes to infinity, everything washes out except for this v hat. Okay, so just to summarize, both the earlier papers of Bergerman, Brooks, and Morris on earlier discussed papers by Bergerman, Brooks, and Morris on the first price auction and standard auctions and DO 2018, they use obedience constraints to get lower bounds on revenue. Okay, so the key difference, so DO, of course, achieves a better bound, at least asymptotically, than the first price auction. And the key difference is that in these papers, we're using non-local constraints, uniform upward incentive constraints, where you're deviating to something potentially much larger than your equilibrium bid. And in DO 2018, revenue is being tied to local incentives, and that allows it to achieve a better bound. So in the next lecture, we're going to pursue this analysis, or Songza is going to pursue this analysis to its logical conclusion and use local incentives and controlling the sensitivity of allocations to actions in order to identify mechanisms that optimize the revenue guarantee without any qualifiers like restriction to standard auctions. So I'll stop there.